Good afternoon. Today I'll be presenting the k-nearest neighbors algorithm, commonly referred to as KNN. KNN is a supervised machine learning algorithm used for both classification and regression tasks. The key idea behind the algorithm is that observations that are close together in feature space tend to share similar outcomes. During this presentation, we'll discuss what KNN is, how the algorithm works, how we measure its performance, and finally we'll walk through a real example using a dataset of BMW vehicle sales. Machine learning algorithms are typically grouped into three main paradigms. Supervised learning uses labeled data where both the features and the target variable are known. Unsupervised learning attempts to discover patterns or structure in unlabeled data. Reinforcement learning focuses on learning optimal decisions through interaction with an environment. K-nearest neighbors belongs to the supervised learning category. K-nearest neighbors is a non-parametric algorithm, meaning it does not assume a specific mathematical form for the model. Instead of learning a global function during training, the algorithm stores the dataset and makes predictions at runtime. When a new observation appears, the algorithm identifies the k closest observations and determines the predictions based on those neighbors. The concept of distance is central to the KNN algorithm because the model determines similarity between observations using a distance metric. The first and most common metric is Euclidean distance. This measures the straight line distance between 2 points in feature space. Think of this as the direct path between two locations. Another common used metric is Manhattan distance. Instead of measuring the straight line path, Manhattan distance measures distance along a grid-like path, similar to how someone would travel along city blocks in Manhattan. Different distance metrics define similarity differently, and the choice of metric can influence how the KNN algorithm identifies its neighbors. The value of k determines how many neighboring points influence the prediction. A small k makes the model sensitive to noise in the dataset. A larger k produces smoother decision boundaries, but may oversimplify the data. Building a KNN model follows a typical machine learning workflow. First, we prepare the dataset and separate the input features from the target variable. Next, we split the dataset into training and test sets. Feature scaling is especially important for KNN because the algorithm relies entirely on distance calculations. In the implementation example, I'll create a scikit-learn pipeline. The pipeline first standardizes the input features using a standard scaler. This ensures all variables are measured on the same scale before distance calculations are performed. The scaled dataset is then passed to the KNN classifier. After training the machine learning model, we then need to evaluate how well it performs. For classification problems, we commonly use metrics such as precision, recall, F1 score, and confusion matrices. These metrics help us understand how accurately the model predicts each class. Another useful evaluation tool is the ROC curve. The ROC curve plots the true positive rate against the false positive rate. The area under the curve, or AUC, measures the model's ability to distinguish between classes. A higher AUC indicates stronger classification performance. KNN is widely used in domains where similarity between observations provides predictive value. For example, recommendation systems often identify users with similar behavior patterns. KNN also can be used in fraud detection, image classification, and medical diagnostics. So in summary, k-nearest neighbors is simple but powerful machine learning. It makes predictions based on similarity between observations within feature space. Although computationally expensive for very large datasets, it remains an excellent baseline algorithm for classification tasks. We're now going to go through an example of a machine learning k-nearest neighbors actual implementation where we take the data in this file that shows BMW global sales from 2018 to 2020 or through 2025. What we're going to do is, based off the features of the data, we're going to predict what kind of vehicle model is seen in the record. So as you can see, we bring in our libraries. We bring in pandas, NumPy, we bring in train test split, our column transformer for our pipeline. We bring in our pipeline, we bring in our standard scaler, label binarize, our k-nearest neighbor classifier, our grid search, our confusion matrix, our ROC curve, AUC curve, and PLT, so our pyplot for matplotlib, and then SNS, so our Seaborn library. We're then going to load those. Now we're going to go ahead and read in our data set. Perfect. So what we're going to do here next is we're going to drop our columns that are not specifically useful towards predicting. So our year is not going to be useful towards predicting, our month and our region are also not going to be useful towards prediction. Those are more so talking about the year of the vehicle, the sale, and then also the region of the sale. So we're going to drop those, and then also from our x-axis, we're going to drop the model because that's going to be our y, or our target value, right? So we'll go ahead and run this, and then we are going to run this where we define our x and our y, and then for our train test split, we're breaking this into 60% to our train data and 40% to our test data. And then we're using y for stratify to help balance out class imbalances. Now here's where we're implementing our pipeline that we discussed in the PowerPoint, where we're using our standard scaler to standardize our column values, so our units sold, our average price and European value, revenue in European, BEV share, premium share, GDP growth, and fuel price index. And then also bringing in our nearest neighbor classifier. So again, this is the pipeline. What it's first going to do is it's going to hit this standard scaler, then hit this k-nearest neighbor classifier. So we'll go ahead and run that. And then for our parameter grid, we are bringing in our KNN nearest neighbor from range from 1 to 21. And then for our weights, we're defining is it uniform or distance. And then for metrics, we're giving the option for Manhattan or Euclidean. And so what we're going to do here is this is going to find the best model to use. It's going to use grid search, feed it through our pipeline, or feed it our pipeline, our parameter grid, CV, our scoring. And so what we're going to do here is we're going to find and create the best model to use moving forward. So we'll see that play out. So we're going to run our parameters and then also run our grid search CV. There we go. Now for our grid fit, go ahead and run that. And so after we fit towards our data, we'll see what it looks like whenever we bring back from our best parameters. So we talked about with grid search CV, we're going to use that to help bring back our best parameters. And so here it tells us that the Manhattan distance is the best form of metrics for measurement, and then for defining our nearest neighbor, or our K value, 19 is going to be our K value. So we listed 1 through 21 as our range for K. And then for our weights, we're looking at the distance here. Now we're going to go ahead and predict with our y. So we made our y underscore predict, so our prediction values using our best model here. Now what we're going to do is create a confusion matrix to show kind of an evaluation of how successful we were per category. So you can see here for Model 3 series, we predicted true, true for 121 of the Model 3 series, predicted 30 for the Model 3 series for many, and so forth. And we can see kind of this diagonal line that escapades down into the bottom right is how we get our true. Kind of gives us a visualization into what our truth looks like, how well we did. Right? But the ultimate truth here is going to be our ROC curve, and we're going to get a very good visualization back from that, and also a good representation of where each model lies, or each value, so how well we were able to predict each. So remember, the higher the number, the better. So we can see here for a Model 3 series, we were almost at 1. For a Model 5 series, we were almost at 1, or at 0.9. We're at 0.848. For our Mini, we were at 0.989. 945 for our X3, 863 for X5, and 1, so perfect for our X7. 0.822 for our i4, iX, we were at 0.986. Remember, as close to 1 as we can get, the better there for our ROC curves. All right. And with that said, that is going to end this video. Thank you for joining me. If you found this helpful, feel free to like this video or subscribe.